Welcome. Today we will start with assignment number 3 and continue our series on concept of thermodynamics, which is a course running on SWAYAM platform under NPTL. So we'll start the first question, which is which among the following statement regarding thermodynamic work is are correct? Okay. So they are asking about, incorrect. Okay. So out of the given four statement, which of the following statements are incorrect? That's what they are asking. Okay. So what is the first statement? Work is a form of energy in transit. So this statement is correct. We can only recognize work only when it transfers from one boundary to another boundary. Okay. So this statement is correct. And work is done by the system if the sole effect on the surrounding could be raising of the weight. So this statement is also correct, as we learn while learning about the work. And work is a form of energy stored or possessed by the system. This statement is incorrect. Why? Because it is a statement about a property, or we can say kinetic energy or internal energy. Because these energies are possessed by body and not a work. Work is a boundary phenomena, and that's what this statement is saying. So this is correct, and only the statement C is incorrect, which is stating that work is a form of energy which is stored or possessed by the system. So work is not stored or possessed by the system. We can say the work is done, means work has been done by the system only when it is what we can say if in some process there is some change, or we can recognize it if it is done across the boundary. Okay, so that's what we can say about the work. And it's not a property. It's not a property of a system, unlike internal energy, which is a property of a system. That's why we can't write delta W as W2 minus W1 as a work done moving from state 2 to 1. While in case of internal energy, we can write U2 minus U1, because it is a property of a system, and this is not a property of a system, and it is a it depends on a process. Okay, so it varies from process to process, and doesn't depend only on the points. That's why we can't write like this. And for internal energy, we have a privilege to uh, write statement like this. Okay, then coming to the second question, what is it stating? So the second question is which among the following statement regarding heat are incorrect? So be careful or mindful, we can say, while reading these questions. So it can be tricky. You may read in hurry it as correct and mark something wrong answer. So just be mindful while reading the question. Okay, so that you mark proper answers. And it is also MSQ type of question. So we need to find out incorrect statement out of the given four. And the first statement is the amount of heat transfer. Before starting, let me state a few things about heat. So like work, heat is also a boundary phenomena. It is energy in transit. It is not stored by the system and varies from process to process, and it is not a point function. Okay, so please keep a note of all this statement. So the first statement is the amount of heat transferred when a system undergoes a change from state 1 to state 2 depend on the path that the system follows during the change of state. So this is the correct statement. And heat is a form of energy that is transferred across the boundary of a system by virtue of the temperature difference between the system and its surrounding. So this is the definition of heat. This is also correct. Third statement is heat is a form of energy possessed or stored by the system. Okay, by virtue of its temperature. So this is incorrect. We can means it is more or like stating about internal energy, not about heat. Okay, so this statement is incorrect with respect to heat. And the fourth one is the amount of heat transferred when a system undergoes a change from state 1 to state 2 does not depend upon the path that the system follows during the state. So it is contradicting the first statement, that is option A. So this is also incorrect. Heat absolutely depends on the path. So statement C and D are incorrect. So C and D are our answer. Okay, I hope you got this. Then coming to the next question, which of the following statement is true about the work and heat? Okay, so both work and heat are a path function, not a point function. Okay, point function is means the change in some function, say f, if it is represented by difference between their values at 2 points, then we can call them as point function. So work and heat can't be represented like this. That's why they are not a point function. Okay. then both are path function. So both work and heat are path function. This is true about heat and work. So option D is correct. Then coming to our fourth question, which is an ideal gas undergoes a compression process in which its volume is reduced to one third of the original volume. So volume at state 2 is one third of volume at state 1. That's what it is saying. Okay. And which process? The question is which process will require a larger work input. Okay. So as the ideal gas is undergoing compression, so it is clear that we need to provide a work from our side. Means work is been work input has to be provided rather than extracting work output. Okay. Because it is a compression process. So they are asking which process will require larger work input. First one is isothermal and second one is polytropic with exponent n is equal to 0.5. So for ideal gas and isothermal process, we can write PV is equal to constant. And for polytropic process which n is equal to 1.5, we can write PV is equal to 1.5 times C. For any general polytropic process, PV raised to power n is constant. Here they are given n as 1.5. That's why I have written 1.5 instead of n here. So this is our second process equation, and this is our first process equation. Okay. Then what they are asking, which will require larger work input. Okay. So for a closed system, we know that area under the PV plot projected on volume axis gives the work done. Okay. So this is for isothermal process and this is for polytropic process. So if we calculate slope for each of these process, and since the initial and final states are not changing, means from V1, okay, we are moving to V2, means V1 and V2 are not changing. So between this line, means between these vertical lines, we can plot the equation for this process and also for this process, and then we can judge by plotting by what we can say by calculating area under the PV plot projected on volume axis. Whomsoever plot has a maximum area under it, we can say it will require larger work input. Okay. So if you know something beforehand about this processes, it will be better. Otherwise, you have to start from first principle. So what we can do is we can take log on both sides. So ln P ln V is equal to ln C. So it will be easier to differentiate. Log of P is nothing but differential of log of P is dP by P. Log of P is dP by V, and it is 0. So dP by dV is nothing but minus what we can say P by V. Okay. So same thing we will do here. If one difference will be there, what is it? Here coefficient 1.5 will came. So ln P plus 1.5 times ln V. I hope you are familiar with the rules of logarithm. If not, let me show it quickly. Ln AB is nothing but ln A plus ln B. Okay. And ln AB or anything like ln A ka power C is given, then we can take this exponent to coefficient side and write it as ln A. Okay. So I have used this property while simplifying this. Then I will differentiate this. What equation I will get? dP by dV is equal to minus 1.5 P by V. Okay. So from both the equation, we can see that slope of isothermal line on PV plot is more than slope of slope of polytropic line on PV plot is more than slope of isothermal line. Okay. So if we have to plot between the same state, then this PV raised to power 1.5 times equal to C will look like this, while isothermal will look something like this. Okay. So we can clearly see area under PV raised to power 1.5, that is area for PV raised to power 1.5 is equal to constant is more than area for PV raised to power constant. So this is for polytropic, this is for isothermal. So area for means area under the curve projected on volume axis for polytropic process is more than that for isothermal process. So polytropic process will require larger work input than the uh, isothermal process. What we can write, which will require larger work input. So polytropic process with n equal to 0.5 will require larger work input. I hope you got it. Then coming to the question number 5, what they have given. If you if you have watched my video on assignment 2, then a similar kind of questions I have solved there. If you have not watched it, you can watch it so that you can get a clear idea how to calculate properties at respective points, and also how to get an equation of pressure at for any given process. All these things I have covered in my previous video, so you can watch it for a better understanding. So continuing with question 5, what they have given, a 100-liter tank A. So volume of tank A they have given 100 liter, which we can simplify as 0.1 meter cube. Okay, because 1 liter is 10 to the power minus 3 meter cube, and contains argon gas of at 500 kPa. So PA at state 1 is 500 kPa. Also TA at state 1 is 25 degrees Celsius. They are given. Okay. Cylinder B having a frictionless piston such that of such a mass that pressure of 250 kPa will float it. So initially pressure means in the tank B, the pressure at state 1 is 0. Okay, and when it floats, okay, so once it floats, only pressure of 250 kPa is required to float it. So what we can conclude from this, that after once it floats, this much pressure is sufficient to float it. So it is a constant pressure process, and anywhere if you get a mass flowing means a freely floating mass, means this mass is floating in the atmosphere only. Okay, so whenever a mass is freely floating against the atmosphere, then that process is nothing but a constant pressure process. Okay, so I will come with this. We can write it as PB at state 2 is 250 kPa and TB at state 2 is 25 degrees Celsius. Okay. After opening the valve, we are getting this state. The valve is open and argon flows into B, eventually uniform state of 250, and also for PA2 also it is 250 kPa, because they have mentioned we are eventually getting a uniform state in both the tanks. Okay, so PA2 is also 250 kPa and TA2 is 25 degrees Celsius. Same for both. So what is the work done by argon gas during the process? Anything I have missed? Let me check. One more thing that they forgot give, but so this tank is rigid. Okay, so that's the one thing, because this question is taken from the previous assignment itself. So there they have mentioned this tank is rigid, and here I think they have forgot to mention that about the rigidity of the tank. So what we can write, VA2 is also 0.1 meter cube. Okay, so that's the one thing. What we can do now, initially what is there, mass at state 1 for tank B is 0, and mass at state 1 for tank A we need to calculate. So we can use by assuming what, argon is an ideal gas, and we can write ideal gas equation as PV is equal to MRT, where R is characteristic gas constant, which is nothing but universal gas constant divided by molecular mass. Okay, so what we can do, for state 1 we can write PA1, VA1, MA1, R bar, TA1. Okay, one more thing you need to be careful about, That is, while substituting the temperature in ideal gas equation, you need to convert the temperature in absolute form. That is by adding 273. Okay, so it would be equal to 298 Kelvin. Okay, then substituting values here, you will get values of Ma1 something. Okay, so this is nothing but mass in this tank initially. Finally, what will happen means at state 2, there will be some mass in tank 2 and some mass in tank B. Okay, so P is given, T is given, V is given, R is known. So we can calculate Ma2. Similarly, P is, uh, P is, P is given here and T is given here and M is given here and V, B2 is not given. Okay, so it is unknown. So what we can do, we can write a mass balance like mass at state 1 Ma1 is equal to mass at state 2. Okay, so how it is coming, because it is from the conservation of mass, whatever the mass we have here, it can't go anywhere. It will either remain in the tank A or it will go in the tank B after we will release valve. Okay, so that's what I have written here. That is, mass at state 1 is nothing but mass at state 2 plus mass in the tank 2, in both the tank at state 2. Okay, so we know for from ideal gas equation, that is PV is equal to MRT. Writing this equation in the term of mass for each of the state, we will get a volume for state 2. So once you will substitute the values, you will get VB2 as, let me check, VB2 we will be getting as 0.1 meter cube and VB1 is 0 because initially it is at bottom, that's why it is 0. And since this tank is rigid, the gas cannot do any work on this tank. So what they are asking is, what is the work done by the argon gas during the process? So work done by argon gas during process is only to raise this piston by the volume equal to VB2 minus VB1, that is nothing but 0.1 meter cube. Means this much change in volume is brought about by argon gas during the process. Okay, so work done by argon gas is nothing but, it is 0 for tank A because it is rigid, and for tank B it is PB times delta V, since PB is constant, or we can say PB times dV from state 1 to 2. Since PB is constant, we can take it outside, and delta V is nothing but V2 minus V1. So PB they have given as, I think, 250 times 0.1, it is nothing but 25 kilojoule. Why? Because this pressure is in kilopascal, that is nothing but kilonewton per meter square, and volume is in meter cube. So kilonewton meter, and Newton meter is nothing but joule, so that's why it is kilojoule. Okay, I hope you got this. Correct answer for this question is 25 kilojoule, which they have given as option C. Then moving forward, okay, so air at, next question, air at 150 kPa and 30 degrees Celsius is contained in a piston cylinder arrangement with the initial volume of 0.1 meter cube. Okay, so they have given for state 1, pressure is nothing but 150 kPa, temperature is 30 degrees Celsius, so 30 plus 273, which we can write as is 303, okay, Kelvin. And initial volume is also given as 0.1 meter cube. And another thing that they are given, inside pressure balance the ambient pressure of 100 kPa plus externally imposed force that is proportional to 0.8. So externally imposed force is Fe, which is proportional to 0.8. So some constant time V raised to power 0.8. And also it is balancing the atmospheric pressure, that is 100 kPa. So kPa, so So there is, let me help you to visualize this situation. So we have this piston cylinder arrangement, air inside it, inside pressure is say P something, externally we are applying P naught, along with it we are also applying Fe. Okay, so what they have mentioned, since we are assuming quasi-static process, so each state is equilibrium, each state is equilibrium. That's why inside pressure is balanced by P naught plus Fe. And they have also mentioned Fe is nothing but equal to 100 kPa. Sorry, Fe is nothing but C times V raised to power 0.8. It is P. P is nothing but inside pressure, that is pressure of a gas. Okay. So having this thing with us at state 2, we can write, I hope this is visible to you. So final pressure is 200 kPa. Anything they have mentioned about volume? No. Okay. They haven't mentioned about volume. So pressure at initial state is known, temperature is known, volume is known, pressure at state 2 is known. If we somehow calculate volume at state 2, okay, then we can also calculate temperature at state 2 by ideal gas equation. Okay, so what we will do is pressure at state 1 is P naught plus C times V1 raised to power 0.8. We can write this. Similarly, pressure at state 2 is P naught times P naught plus C into V2 raised to power 0.8. Since we do not know, we can do it in either ways. Means by solving this equation, first calculate C, then calculate V. This can also be done, but the most what we can say convenient way to do this is let me bring P naught on this side, that is P1 minus P naught, and V1 raised to power 0.8 on this side, so we will left with C. Similarly, we will do P2 minus P naught and V2 raised to power 0.8 times C. Okay, so what we will get is, we can write it as P2 minus P naught V2 raised to power 0.8. Then once we have this equation with us, what we need to find? V2. So V2 is nothing but V1 0.8. V2 is V1 P2 minus P naught and P1 minus P naught. P2 P1 P1 P naught P naught, everything is known to us. P naught is 100 kPa. They are given. Then taking 1 by 0.8 root on both sides. So V2 is equal to V1 times P2 minus P naught, P1 minus P naught, whole raised to power 1.08. Okay. So with this you will get V2. Once you will get V2, since it is a closed system, okay, because nothing is flowing outside the system. If we assume this as our boundary, so we can say mass is conserved, means mass is not changing, and since air is also, and since the temperature changes are not so high, assuming it, so R means characteristic gas constant is also not changing. That's what we are assuming. So it is also constant. Okay. So since M is constant, R is constant, we know that PV is equal to MRT. We can write PV by T is equal to constant. Okay. Oh, it's very messy. So, what we got, PV by T is equal to constant. That is P1 V1 by T1 is equal to P2 V2 by T2. From here we can get T2 as something. So T2 we will get in Kelvin as we check it will come out as 961.996 Kelvin, and once we subtract minus 273 from it, we will get 11 minus 3 7 273.15 we need to subtract. I think that should not make any difference. Let me do it. 961.996 273.15. Okay, so it is 8. 10 out of 7 is also 8. 7 8 minus 2 is 6. Okay, So it will come out as 688.85 degrees Celsius. I hope you got this. Then next question is, what is the work done by the air during the process? Okay. So since what I have mentioned in the above question too, that is since air is freely piston is freely floating in atmospheric pressure, the process will be constant. Wait a second. Sorry, this is not a constant pressure process. Why? Because air is no piston is not freely floating, because external forces imposed on it. So it is not floating freely. That's why it is not a constant process. The governing equation of a pressure is P is equal to P naught plus C times V raised to power 0.8. Okay. Uh, so value of C can be calculated from any one of the equation that I have written above. So that we will be having with us P is equal to P naught plus C times V raised to power 0.8. And we know that work done from state 1 to 2 is nothing but integral P dV for a closed system from 1 to 2. And P is nothing but P naught plus C V raised to power 0.8. It's a simple integration. Everyone can do it. So it is P naught times V2 minus V1 plus C V raised to power zero point 0.8 plus 1, zero point 0.8 plus 1 from 1 to 2. P naught V2 minus V1 plus C times it is V2 1.8 minus V1 1.8 or 1.8. So this is nothing but work done from state 1 to 2. P naught is known to us, V2 minus V1 we have calculated. Similarly, C we have calculated. So after this we will get answer as is 24. Okay. So A will be the correct answer for this. I hope you got this. Then question number 8. So what they have given is a piston cylinder shown in the figure contain 1 kg of saturated liquid plus vapor water. So at state 1, saturated liquid plus vapor water. Okay. So mass of water is nothing but 1 kg, and since it is a closed system, mass will not change. Okay. Remaining quality at state 1 is 15%. I hope you are aware with this quality and all terms, and also this saturated liquid and saturated vapor, all this concept. If not, you can watch my previous videos where I have mentioned this terms in a greater detail. Okay. And also pressure they have given us 200 kPa. All these things are for water. Okay. The mass of piston is such that pressure of 400 kPa will float it. So what does this mean? Uh, Suppose this is resting on a stove. Okay, we are adding heat to it. We show it properly on a PV plot. You will understand it in a better manner. That drawing. So this is our volume axis. This is pressure axis. Okay, so we are somewhere here. Let's say that is our state 1. What will happen is till pressure of 400 kPa, we are now at 200 kPa. Okay, so this will only float after 400 kPa. Okay, so so once the pressure inside the system reaches 400 kilopascal, this piston will start floating. Okay, means till this point, let's call this as point A. Okay, say any intermediate point. So till this point, this will not float, okay, because the pressure inside is not sufficient enough to overcome the resistance due to mass, okay, and due to this stops. That's why it will not float. And after 400 kPa, it will start floating because pressure will balance this whatever the resistance is created by this mass, okay. And water is slowly heated after this also, means what they have mentioned that mass of the piston is such that the pressure of 400 kPa will float it, that's fine. And water is slowly heated until it exists as saturated vapor, okay. And it is continued to hit till it hits this line. So this is our final state, or we can say state 2, because this is nothing but a saturated vapor line. Here we will get saturated vapor, and that's what they have mentioned. What is the work done by the water during the process? Okay, so for a closed system, work done is nothing but PdV. Okay, and from state 1 to A, it will be 0. Why? Because dV is 0, because volume is not changing. And for A to 2, we will get PdV. It is nothing but pressure will not change, and our moment is like this. So dV is nothing but delta V, that is V2 by V1, V2 minus V1, or in this case V2 minus VA. Okay, so this is the work done that we need to calculate. Okay, so they have given, means V2A, how can we calculate? Since V1 we can calculate from the table, at 200 kPa we can calculate Vf and Vg. From there we can calculate V1 as Vf plus X times Vg minus Vf. From the table, pressure table, we can look at 200 kPa, and in that row we will find Vf value and Vg value at 200 kPa. And for X is equal to 15%, that is X equal to 0.15. Here we need to put in fraction, not in percent. Okay, so we will get the value of V1. So V1 will get from table as, let me check, it is 0.13376. So once you will read it from the steam table, 13376, and be mindful about the units. It is meter cube per kg because it is specific volume, and we are concerned only with the work done from state A to 2, and that's why. And because the property at state A we can't calculate directly, that's why we are calculating it at state 1, because the quality at state 1 is given, and specific volume at state 1 will be equal to specific volume at state 2, because from 1 to 2 it's a constant volume process. So we have got value of V1, which is nothing but equal to VA. Okay, and how we will get V2? So at 400 kPa, from steam table we will get V2 as Vg at 400 kPa. Okay, so this value from the steam table is nothing but 0.46246 meter cube per kg. Okay, so V1 is known to us, V2 is known to us. So work done from state 1 to 2 is nothing but 1 to A plus A to 2. This is 0. I will explain why it is 0. And from A to 2 is nothing but pressure at state A or pressure at state 2 times V2 minus V1, or V2 minus VA, sorry, V2 minus VA. Pressure at state A or pressure at state 2 is equal because it is a constant pressure process, because after this piston will float freely. Okay, no other resistance other than atmospheric pressure is present here. That's why we can write it as P2 is 400, V2 and V1 are given, V2 minus V1, and finally we will get answer as C. Okay, after solving you will get this. No, one more thing that is missing here. You will get this is in kilojoule per kg. Why? Because this is specific volume, and when we will multiply it by total mass, since you are lucky here, you are not, I am lucky here, because if this question was given to me in exam, and I could have marked it as this, even after calculating this I have got full marks. but if they have changed a mass a little bit, then I might not get the credit for this question. Okay, so be careful about the units. It is in kilojoule per kg, and you need to multiply it by total mass in order to arrive at this kilojoule. I hope it is clear to you. Then coming to the question number 9, uh, that is a 5 kilogram of water. Okay, it is also water and mass is 5 kg. It will not change. I've told you why, because it is a closed system. In a piston cylinder device, okay, it's visible here, it's closed system. Okay, that's why I assume it is a, not assume, because it is clearly visible, it's a closed system, closed piston cylinder arrangement, no other, no outflow or inflow is taking place, so it's a closed system. So mass is 5 kg contained in a piston cylinder device as shown in the figure. Piston is massless. Okay, so this is massless, and it is loaded with a linear spring with outside atmosphere of P naught. Outside atmospheric pressure is given. Initially, the spring force is this much with a volume this much. A spring force is 0. Okay, so let me draw FBD of a piston at any intermediate state. So inside pressure will be P naught. So force due to inside pressure will be equal to. So in the above, means in the previous questions, I have balanced just pressure rather than balancing forces. So uh, what I can say, please be careful while doing these things. Let me show where I did this. Okay, so what I did here was I have directly balanced the forces rather than multiplying pressure with area and then with the area here. Why I did this? Because everything is covered up by this constant. Okay, so even if I've multiplied it with area p naught plus c times v raised to power 0.8, so it will be equal to p naught plus c times a v raised to power zero point 0.8. P is equal to p naught plus c1 times v raised to power zero point 0.8. So only this constant will change, and the way to calculate this constant will not change. The way we have calculated it earlier and the way we have calculating it now will remain same. So this will also not change. Okay, so whatever we have did is correct. So only for this question. Okay, so for other questions be careful. We have to balance the forces, not pressure. Okay, so that's what I want to mention here. Then coming back to here, so here is our inside pressure times area. Similarly, outside pressure times area, and since it will expand after heating, okay, heat is now added. So after heating, it will expand. So the restoring force will act downward, which is nothing but K times X. Okay, X is nothing but it's a displacement. Means suppose it is, you can say, at any state X, this X is measured from this reference, say bottom of the cylinder. Okay, this is our reference. So it won't be of any use while solving the problem, but still I have mentioned it. So P naught they have given is equal to P1, means pressure at state 1 is nothing but 100 kPa, and corresponding volume at state 1 is nothing but 0.1 meter cube. Similarly, heat is now added until the piston hit the upper stop, at which the volume is 1.621. So at state 2, V2 is nothing but 1.621 meter cube. It is just hitting the stop. Okay, just hitting, means the governing pressure equation that will means the relation of the pressure that will calculate from pressure force balance will remain valid if it just hit the stop, and if it touches the stop and remains there and we are still adding the heat, so this equation will no longer be valid. So once we balance the forces, we will get PA is equal to P naught A plus KX. Okay, so P will be equal to P naught plus K times A into X. So I will tell you how to make use of this equation. So volume is given and pressure is also given. So P2 is given. So pressure is known and volume is known, and since mass is known, we can calculate specific volume at state 2, which is nothing but 1.621 times 5. After calculating, it will come out as some value, and once we will know pressure and volume, so from table, let me check. It is nothing but volume is 0.3242 meter cube per kg, and for this pressure and this volume, it lies in a superheated region. You can check it from the table, because this pressure will be far less than the pressure corresponding to this, or what we can say, rather than putting it like this. Suppose, let me explain you with PV plot. This here. So this is our volume at state 2. This is our pressure at state 2. Okay. So at this pressure, if you calculate saturated volume, means saturated volume of the saturated water or saturated liquid, the what you will find that V2 will be far larger than Vg. Okay, means here volume at a volume of saturated liquid is less than volume at state 2. What does this imply? Means volume of gases is typically more than that of any other uh, in any other state. Okay, so what we can conclude from here, this state lies in a saturated or we can say, sorry, superheated region. Okay, so as this state lies in the superheated region, we have V2 with us, V2 with us, and what's the question for us is, what is the temperature inside the cylinder when the piston just hits the upper stop? Okay, so they asked us to calculate T2. Since P2 is known to us, V2 is known to us from superheated steam table, we can calculate T2 as 300 degrees Celsius. Okay, so B is the correct answer. If you are not getting this answer directly from the table, what you can do is you can interpolate and get the result. So after interpolation, you will get the same result. And how to do the interpolation, you can watch my previous videos. There I have explained in details about the interpolation. Okay, so that's the answer for this 9 question. And the sub part, same sub problem for the question is, what is the work done by water during the process? So let me plot the process first. Since we know that P is equal to P naught plus some K by A square times X. Okay, or sorry, K by A times X. So P is equal to P naught. I have derived this above, and multiplying, dividing by A, we will get AX, and this AX can be written as volume. How? X is height, and this is area of the piston, and at any distance x, it will be nothing but equal to volume at that given x. So P is equal to P naught plus K by A square times B. Okay, so what we can write from here? P naught plus CV, where C is nothing but K by A square. So from here we can see that pressure is proportional to volume. Okay, so and with a positive intercept, so we can draw a line like this, where this can be our state 1, with the pressure P1 and volume V1, and this can be our state 2 with pressure P2 and volume V2. And we are very well clear with this, that work done from state 1 to 2 is nothing but area under PV plot projected on volume axis. Okay, so this is nothing but area of trapezium. So this much part is P1, height is P1, this height is P2, and this is nothing but V2 minus V1. So it is half times sum of heights times perpendicular distance between them. So this is nothing but the formula to calculate area of trapezium. Okay, so we have given half. P1 is how much it was? P1 is 100, it is 800. V2 is 1.621 minus V1 is 0.1. Okay, from here we will get 684.45 kilojoule. It is in kilopascal, it is in meter cube. Okay, because we have mentioned total volume here, not specific volume, that's why the answer will be in kilojoule. So it is 684.45 kilojoule. So I hope you find this video useful, and thanks for watching, and join me for more content related to mechanical engineering like this. So thanks.